Hi guys, welcome back to 7 Steps to a 7 in Olympiad number theory. In the last video, we were exploring divisibility and GCDs and how they can be used to solve NT problems. And in this video, we're going to be continuing our discussion of that by going over what are called size arguments, where we somehow use the size of certain numbers to our advantage. And in a way, size and divisibility are incredibly related to each other. I think they're the two sides of the same coin in the way that size arguments can help us solve divisibility problems. And likewise, divisibility insights can give us ideas on size problems. Anyways, let's go ahead and see how the basic framework of size arguments work. So first of all, suppose that m divides n. Then what can we say? Well, we know that n can be one of the multiples of m, of course. So it can be something like 0, m, negative m, 2m, negative 2m, so on and so forth. Now, if we're looking at size, then this 0 case here doesn't seem to be relevant much. But for the other ones, it seems like we're always going to be something larger than m. And we can pinpoint exactly how this happens. And this means that absolute value of m is less than or equal to absolute value of n. Now, of course, this is a very weak bound because we can obviously do a lot better than that if we eliminate these two as well. So that's one idea. And the other idea is that if a divides n for infinitely many a, then that means that n is equal to 0. And how come this is true? Well, if n is not 0, suppose that n is 49 or something like that, then there's going to be some number in this infinitely many that is greater than 49. And that will give a contradiction according to this. So these are the main two theorems that we need to know. That if m divides m, then the absolute value of m is less than or equal to the absolute value of n, which is a very stupid bound, but it often works for our purposes. And if a divides n, then n equals 0, if this holds for infinitely many a. So suppose we have two expressions f of n and g of n, which are both positive integers in terms of n, such that f of n divides g of n. Then this means that we know that f of n is less than or equal to g of n. Then what does this mean? And how can we figure out when will this cause an issue? And to answer this question, we must explore what are called orders of magnitude. So what exactly is an order of magnitude? Well, I think it's best if we demonstrate by example. So suppose that we know n cubed divides n squared plus 7600. What are the possible values of n? And note that this is a divisibility problem. So we can see how size helps with divisibility. So let's try testing out some small values of n. For example, n equals 1 obviously works since 1 divides anything. N equals 2 gives 8 divides 7604, and that doesn't work. But when n equals 4, we get 64 divides 7616, which just so happens to be true. And now this makes us think that because this right-hand side is much larger than this left-hand side, it will hold true for infinitely many n. But let's take a look at a larger value of n. For example, n equals 100. Then this one here becomes 1 million. And this one here becomes 10,000 plus 7,600, which is 17.6 thousand. Now, 1 million is way larger than 17,600. So we're going to be running into an issue immediately where this cannot happen. So in general, we know that n cubed by this logic, grows much, much faster than n squared plus 7,600. We just need to figure out how this ends up working out in the end. And to see how this works out and make the argument formal, let's do this. If n is large enough, suppose n is greater than 20, then this means that n cubed, we want to turn it into an n squared thing with the dumbest bound we can make. So this becomes greater than like n times n squared, and n is greater than 20. So this is 20n squared. And this is greater than n squared plus 7,600 for all n greater than 20. And therefore, because n cubed is greater than this side here, we will run into an issue. And therefore, we must solve the question whenever n is less than or equal to 20. And an exercise is to solve this on your own. And you can either bash out all the values less than or equal to 20 if you're really, really bored, or you can try finding the shortcut. There is a shortcut, so yeah. And the point is that because n cubed grows way faster than n squared plus 7,600, we're just going to run into an issue and the divisibility will fail. And this gives rise to the following heuristic. So if the left-hand side has a larger order of magnitude than the right-hand side, then we know we're going to hit an issue very soon. And we just have to figure out how that issue will happen. Now, here are some common orders of magnitude for you to know about. The first and most common one is going to be polynomials and general powers of x. And it is that polynomials of degree r always grow faster than polynomials of degree s whenever r is greater than s. And we kind of hinted toward this idea in the last video when we were exploring polynomials. And another very, very cool thing is that all of these guys grow slower than exponential functions. So for example, this means for very, very, very large n, that 1.000001 to the n is greater than n to the 1000000. Now this should come off as a huge surprise because this side here seems to grow very, very slowly, and this side here seems to grow very, very quickly. But this will eventually overtake this one. And this is a very profound consequence. And one final thing is that the factorial function, factorial and factorial, grows faster than this as well. So the point is to know your order of magnitude, because then you're able to see how to use the size issues here. So what happens if we have A divides B and the order of magnitude of A is less than the order of magnitude of B? Then we won't run into an issue immediately and we have to do a bit more work. So how can we exactly control these orders of magnitude? Well, there are a few different ways to do it, and well, there are many, many, many ways to do it, and in this video, I'm going to be exploring the two most common ways. And the first way is the Euclidean algorithm. And the reason why the Euclidean algorithm works is basically what we were exploring in the last video. Suppose we have something like n squared dividing n to the 100 plus n. Then the order of magnitude of this one, this has degree 2, while this one has degree 100. So it seems like there's no way to control what will go on in this. However, here's where the idea of Euclidean algorithm comes into play. Because we have n to the 100 is equal to n to the 98 times n squared, we know that n squared divides this one, which means that we can eliminate it. And this gives n squared divides n. And notice how we were using the Euclidean algorithm here. And now look, we have n squared divides n, the degree of this is 2, the degree of this is 1. So this has a larger order of magnitude than this one. And this means that we're going to be running into issues. And indeed, we have n squared is greater than or equal to n for all positive integers n, which means that n equals 1. So the point of this is that we can use the Euclidean algorithm to reduce the orders of magnitude. And let's take a look at an example from the IMO shortlist to see how this principle applies in actual Olympiads. Now you might recognize this problem here from the video 3 handout, and that's because it was on the handout. However, I'm including it in this video because I think it really highlights some of the principles about using size arguments in Olympiads. So if you haven't already tried it, go ahead and try out this problem, and go ahead and pause the video and try it out on your own. And when you're ready to discuss, hit the play button. Okay, so let's go ahead and discuss this problem together. In the video 3 handout, I gave the hint where you had to subtract the quantity a plus 3 from both sides. And let's see how you would motivate this idea. So first of all, how do we even think of going about this problem? The thing that stands out first is that because n here is an integer, a squared plus b plus 3 divides ab plus 3b plus 8. And now we want to solve this. So let's try looking at this from a's perspective. So for 1, we have a squared divides this one here, and the degree here is 2, while the degree here is 1. So by a heuristic, that means that some size issue is going to happen. So size involving a. However, this makes us think that if a equals 5, for instance, because we want a large to get a contradiction, this means b plus 8 divides 5, or it should be 8b plus 8. And this should, I think that should be b plus 28. And this could obviously have a solution if you get rid of all the factors of b, and that just gives it. So trying to do things while bounding a won't really work here, because then we have to solve this equation for b, and it might become too complicated. However, we can try instead looking at b now. So for 1, we have the degree here is equal to 1, and the degree here is also equal to 1, because this is b times a plus 3. And now that this means that we want to somehow eliminate this factor of b here, so that this one becomes constant with respect to b in a way. And the way we do this is by using the Euclidean algorithm. So this becomes ab plus 3b plus 8 minus, and now we end up subtracting a plus 3 times b, because that will get rid of this one here. And we also have to do something like a squared plus b plus 3, because we can't just subtract by b. And when we end up doing this, we get a squared plus b plus 3 divides, I think, negative a cubed minus 3a squared minus 3a minus 1, if you expand it out. And now we have that this side here is entirely in terms of a. But wait, this is just a very familiar expression. It is just negative a plus 1 cubed. And we can just get rid of this minus sign over here. So therefore, we know that this quantity here divides a plus 1 all cubed. And because of this, we want to now somehow use the fact that it's not divisible by a cube of a prime. And by considering new p's, we end up getting that new p of a squared plus b plus 3 is less than or equal to 2 for all primes. So that means that if it divides a plus 1 cubed, then that means that it should divide a plus 1 squared if you just work it out. So this gives a plus 1 squared. And when you expand it out, we get a squared plus b plus 3 divides 8 squared plus 2a plus 1. And now this looks very, very interesting, because now we can try bounding it in terms of a. Because now we have an a squared here and an a squared here. The degree of both sides is 2. So let's use Euclidean algorithm again. And this time we can subtract a squared plus b plus 3. And when we end up doing this, we get, I think it's 2a minus 2 minus b. And now look, we can try using size issues regarding a now, but we don't know if this will work exactly, because it didn't work before. But unlike before here, note that the coefficient of a over here is b, and that was what caused the issue. This time it's 2, which is a fixed value. So that means that regardless of what the value of b is, this quantity here will grow astronomically larger than this one very, very fast. So we basically know that something weird will happen, and we just have to work out the details. And let's go ahead and assume for now that 2a minus 2 minus b is not 0, because that's the weird case when trying to use divisibility. Then if it's not 0, then that means that the absolute value of this is less than or equal to the absolute value of this. So 2a minus 2 minus b. And then there are two cases to consider, because this absolute value here can be eliminated. If we end up having that it's less than or equal to the positive one of this, if the absolute value gives a positive number, or I meant the number in the absolute value is positive, then we get something like this. And when we end up solving this, we discover that 2b is less than 2a minus a squared minus 5. And but this is going to be always less than 0, because we can, if you want to, we can write it as negative 4 minus a minus 1 squared. And but you can just kind of figure that it will just go down to minus infinity. So therefore this case doesn't work. Now what if it was instead b plus 2 minus 2a? Then this cancels out here, and what we're left with is a plus 1 squared is less than or equal to 0, but that implies that a is equal to negative 1, because then this is 0. And that's bad. So therefore, we must end up having that b, or should be 2a minus 2 minus b is equal to 0, or b equals 2a minus 2. This is very, very useful information, and we use size arguments to get there. And now let's try plugging back into this expression here, because it seems like we can do a lot with that. And when we do so, we get n equals a times 2a minus 2 plus 3 times 2a minus 2 plus 8 over a squared plus 2a minus 2 plus 3. This one here becomes a plus 1 squared. And this one on top here, if you end up expanding it, is 2a squared plus 4a plus 2. But you might recognize that this is 2 times a plus 1 squared over a plus 1 squared. These guys cancel out, and therefore n is equal to 2. How on earth did this end up working out? Wait, what? This means that the only n which can ever work is n equals 2 by an absolute miracle. But wait, we have to check that n equals 2 can actually work, as otherwise our proof is incomplete. But fortunately, by setting a to be something random and using b equals 2a minus 2, this is not bad. For example, we can set a equals 2 and b equals 2. And a squared plus b plus 3 is then 9, which is not divisible by the cube of a prime. And therefore, we have proven that the only value of n which works, and we have checked that it works, is n equals 2. And for the very reason I discussed earlier, where getting n equals 2 is an absolute miracle. The miracles which happen in order for this problem to work out is why I love this problem so much, and it's one of my favorite problems. It also combines a lot of number theory ideas, for example, looking at the prime exponent over here in this step, and also using size arguments and divisibility. Now let's look at the second idea. And this idea is that, let me go ahead and draw here, is that primes are your friend. And what do I mean by this? Well, we already know from the very start of this entire course that primes are some of our favorite numbers in number theory. And this property that you're going to see here will make you love primes even more. And it is the following. If P divides AB, then either P divides A or P divides B. And this is very, very useful because, for example, if we know that P divides AB, and this has suppose degree 3, this one has degree 4, and both A and B have degree 2, then even though the order of magnitude of this side is less than the order of magnitude of this side here, that means that P divides either A or B. And because both of these are 3, 2, and 3, 2, because P is a prime, we're going to be running into issues. And this is how primes can be useful. Now let's go ahead and take a look at a very specific example regarding primes. And here it is. And here it is. Find all positive integers s greater than or equal to 4, for which there exists positive. And here it is. Find all positive integers s greater than or equal to 4, for which there exist positive integers a, b, c, and d, such that s equals a plus b plus c plus d, and it divides abc plus bcd plus cda plus cdab. Now go ahead and try out this problem on your own and pause the video to try it. And when you're ready to discuss this problem, hit the play button and we'll discuss it together. Okay, so hopefully you've tried out the problem by now. So let's go ahead and do it together. So let's see how we can explore this idea. We're not going to worry about S right now because the main condition that we want to worry about is A plus B plus C plus D dividing ABC plus BCD plus CDA plus DAB. And we want to somehow use some of the similar ideas that we used earlier, where we use the Euclidean algorithm. So with that in mind, let's go ahead. And we want to somehow use the Euclidean algorithm idea from before. So with that in mind, let's go ahead and try writing it as follows. ABC plus D times AB plus BC plus CA. So in a way, we're singling out on the D. And we can go ahead and use the Euclidean algorithm to remove the D, and we get A plus B plus C plus D. Ends up dividing, this should be ABC minus then AB plus C, BC plus CA times A plus B plus C. And this is supposed to be A plus B plus C plus D, but we canceled out with this term here. So we end up getting, it divides this. And when we expand the entire thing out, we get A plus B plus C plus D divides negative A squared B minus B squared A minus B squared C minus C squared A minus, or C squared B minus C squared A minus A squared C minus 2ABC after we expand the entire thing out. And you might notice that, and this might seem like a huge leap of faith, that this expression here is just minus A plus B B plus C, and C plus A. And if you're wondering how on earth one would see this, then I honestly don't blame you. And to get the intuition on how we can exactly do this, I'm going to have to redirect you to the algebra course, which is coming very soon. Anyways, we now have A plus B plus C plus D divides this expression here. So now what can we do? This on its own doesn't really seem to be much different from what we had before, because the right-hand side still has total degree 3. But let's try using primes to our advantage. Suppose that A plus B plus C plus D is prime. Then by the idea we said earlier, that means that this must divide one of the three factors. Either A plus B plus C plus D divides A plus B, it divides B plus C, or it divides C plus A. And well, all of these cases fail because this one here is greater than all of these guys. So therefore, that means that all prime n fail, and S cannot be prime. So what if S was composite instead? Well, if we want S equals A plus B plus C plus D equals Mn for some integers m and n greater than 2, then we want to somehow get a factor of m and a factor of n here. So we could try setting this one to be m and this one to be n. And this means that A is equal to m minus b, and C is equal to n minus b. And we also have b equals b. And when we solve for d, we end up getting d equals, because the sum of all of them is mn, it's mn minus m minus n plus b. So therefore we have that the ordered pair m minus b, b, n minus b, and mn minus m minus n plus b just does the trick. But we don't know what b is, and we want none of these numbers here to become negative, as otherwise we're going to get an issue. So therefore we must have that b equals 1 in order to make all the issues go away. And we therefore get a construction for S composite is m minus 1, 1, n minus 1, and then mn minus m minus n plus 1. They all sum to mn, which is the composite number we need, and we know that it should end up satisfying the condition. And indeed, if you plug it back in over here, we end up seeing that it does. So usually I have a final example at the end of the video, and that's been true for almost every other video in the series. However, because I've already covered many hard examples that demonstrate our key properties, I'm not going to go ahead and go through one last example here. And instead, I'm going to go ahead and let you guys work on the exercises. And some of the exercises shouldn't be too hard, but a lot of them, especially the later ones, are meant to be very challenging and test your knowledge of divisibility and size especially. So good luck on those problems. And as always, if you're stuck on a problem, feel free to drop a comment on this video and I'll be happy to help you. So thank you so much for watching this video. Please subscribe if you'd like to see more, and I'll see you guys in the next video.